Hello, good evening, everyone, and welcome to this webinar on multi-room RF systems. In this webinar, we will be discussing the correct method, the correct tools in order to deploy a successful multi-room RF system. When we say multi-room, we're talking about corporate meetings, we're talking about boardrooms, we're talking about rooms in close proximity and how to enable your RF to work in all rooms simultaneously. So in this, we're going to discuss a few topics. First is spectrum efficiency, which is basically how to enable a large number of channels in a small spectrum, and also how to manage a large number of channels in a small area. Next, we'll discuss a topic called link budget, which actually is helps you calculate the components that are required in order to do a good multi-room setup. We're going to discuss the various components that are required, and then we will take a look at some multi-room, real-world situation multi-room example. Now, first, let's have a look at spectrum efficiency. And just to make things easy to understand, on the left, I have an analog system, and on the right, I have a digital system. And as you can see, I've got about 9 transmitters, which are placed 6 feet apart on the analog and on the digital side. As you can see, everything looks fairly clean, and this is the ideal situation. This is the more practical situation where you have a lot of the transmitters in close proximity. So when you think of a corporate meeting room, a breakout room, you very often have like round tables with a lot of speakers around the table in quite close proximity. And now, as you can see, that the digital spectrum looks still very clean, but the analog spectrum is now pretty noisy. And this is actually what it looks like. If you use a spectrum analyzer, you can see that in the digital space at HD mode, at 10 milliwatt to 1 milliwatt, there is a difference of about 10 odd dB between the analog and the digital. And why this is important to note is usually when you get into, now that we are in the world of digital, when you get into these kind of setups, the preference is to go digital. And this is what the entire spectrum looks like in HD mode. 8 megahertz is the TV channel size for India. And with our top line product like Axion Digital and ULXD, you can fit in about in the range of 63 devices in an 8 megahertz spectrum. We also need to take care of some wireless best practices. These best practices are essential now, whether you're doing multi-room setups, single-room setups, concerts. These are very, very important to remember. First is place your antennas above the audience and away from any obstructions. Okay? The human body tends to be the biggest absorber of RF energy, and having the antennas not at the correct height will actually result in a lot of the RF energy being absorbed by the audience. And this is something we want to try and avoid. So take at least about 5 or 6 feet of height. The more, the better in this situation. Also try and place the transmitters as practically close, the antennas as practically close, but just make sure that you don't overload the front end of the receiver. So in an ideal situation, you need at least about 6 feet from the receiving and transmitting antennas. Try and get them as close as possible for the best RF reception. place them away from sources of interference. And now these sources of interference can be LED walls, can be lights, can be LED TVs, neon lights, etc. So try and have your antennas away from any of these sources of interference. And finally, use directionality of the antenna to your advantage. Make sure the antennas are pointed in the right direction. Make sure you make use of the forward gain of the antenna to your benefit. Have the antenna pointing in the direction you require, and that's the best case scenario and the best way you can make use of the forward gain of the antenna. Now we're going to have a look at the subject called link budget. Link budget is basically a small formula that you should have handy, and this basically gives you the final receiver power value that is required for a successful RF system. Now, in a very broad sense, this is the formula. So the received power is equal to the transmitted power plus whatever gains you might have on the way. So like inline amplifiers, antenna amplifiers, minus the losses. So various losses can be the most important first cable loss. Also very important is the free space loss. Loss due to additional devices in the signal path, so like passive combiners. Okay, so in the broad sense, this is the formula. If you guys need some time, you can just note this down. So you can just put received power is equal to transmitted power plus gains minus losses. And this is taking the formula to a little more detail, where we can actually break up the various gains and the various losses in the system. So the power received, that's denoted by PRX, will be equal to the power transmitted plus gain of the antenna. You could consider this also either forward gain, or if you have an amplifier on the antenna, you could consider the value of the gain on that amplifier. From this, you would take away the LTX, which is the losses from the transmitter cable / connectors. Yeah, you would take away free space path loss. You would take away miscellaneous losses because of fade margin and polarization crossfade. You would LM, that is miscellaneous losses, those generally are not too large, but it's something that you also need to consider. And you can actually get the miscellaneous losses number more if you have like a spectrum analyzer. That's actually the only way you'll get that figure. And to this, you'll add the receiver antenna gain. Again, if there's a forward gain, if there's some amplifier on the antenna, and minus, again, the loss from the receiver side connectors and cables. Yeah. So both are the same formula. One is a more broad based formula, and the second one is in little more detail. Now let's take a look at the main distribution components. First and foremost, and the most important, is a 50 ohm BNC coaxial cable. And it's very important that it's 50 ohms because the radio frequency impedance is all the equipment is designed with the cable being 50 ohms in mind. The problem with using a 75 ohm cable is that all those numbers and calculations which are done to design the device now don't apply anymore because the impedance of your cable is different. So most importantly, the first thing is to use a good quality 50 ohm BNC cable. Most recommended is the one down here, is the RG213U. And if you have access to the RG213U low loss, even better. Very important to remember that signal loss occurs in cables and in connectors, in both. And also, if you use all your components need to all be rated at 50 ohms. So again, you cannot use a 75 ohm BNC adapter, 75 ohm, BNC video splitter, because that changes all these calculations and they are very, very inefficient. Very important number here is the entire loss through a single channel. You want to be kept at under 5 dB. Best case scenario is 3 dB, and acceptable, I would say, is under 5 dB. And at all instances, avoid over-amplification. Over-amplification is simply what happens similar to over-amplifying an audio signal. You distort it. It doesn't sound good. Similarly, you over-amplify and you distort an RF signal. It's something that has to be avoided at all circumstances. These are some of the most common cables that are used. These are all Shure cables and a small loss comparison. So you see in the first column here, you have the Shure model number, length, the general type, trade model number, and you have a loss at 200 megahertz, loss at 600. So most charts you will always see like this. For us, practically, we are not concerned with the 200 megahertz list. Our concern is 600 megahertz. Yeah, so as per the previous slide, we saw the RG213U gives you 6.2 dB loss. This is all measured at 100 feet or 30 meters. Now, yes, 100 feet, 30 meters is a long distance. And to basically make up for this gain is when you would add an inline amplifier and set that inline amplifier to a +6. So the +6 and the loss of 6.2 would basically even it out. So very important to remember that you have to, as much as we would like to avoid it, we have to calculate. These numbers are very important to be calculated. Now this is a chart for the 2.4 gigahertz frequency range. This is not so important for us audio guys, but it's very important for the systems integrators, because system integrators are dealing with 2.4 gigahertz. They're dealing actually with a combination. It's 2.4 and in the 600. So all their conferencing systems are all 2.4. Whereas if they integrate like say a ULXD system or a QLXD or like Axiom Digital with the conferencing system, then they're dealing with both the lower UHF and the 2.4 gigahertz. So again, this chart is very important for the systems guys. And again, coming back to this is this chart basically gives you the premium cables available. So this RG213U low loss made by Times Microwave, the model number is LMR 400. And now if you see this gain, this is just 3.1 dB of loss. So yes, it's an expensive cable, but then so is your equipment. And we should not be skimping on using inefficient cable and saving a little money there as opposed to using a great quality cable, because your entire system basically depends on the accessory. So it depends on a proper antenna. It depends on a good quality cable. So this is very, very important. All right, one of the first components we need to see is the UA834 inline amplifier. Sorry. So what is an inline amplifier? Basically, you have long cable runs. You need to make up for that, the loss in that cable run, using an inline amplifier. It has two gain settings, which is 6 and 12. and you basically calculate the amount of loss along the cable, and you make up that loss with the inline amp. Now, it's meant for remote mounting near the antennas. You can use it along with a UA845 or a UA844 plus distribution amplifier in a very large installation kind of sense, and that we'll see in some of the examples which are about to come. And also through this amp, you get 10 to 15 volts of DC bias from a coaxial connection, which equates to around 0.6 to 0.72 watts. So again, number one is still the cable. Number two would be the inline amplifier. And number three is the UA bias T. Now, what the bias T actually does is it provides a 12-volt DC bias to an active antenna or an inline accessory. Why is this used? Because there are devices, Shure devices, which do not provide antenna bias. For example, the SLX or the QLXD, they don't provide antenna bias, and you can have this device. It's powered by a wall socket. You have this device inline, and you can now power power your antennas, or it's also used to power your inline amplifiers. So using one of these devices, you can power up to 3 inline amplifiers, or 2 inline amplifiers and 1 active antenna. Okay, so why this is important is because as your cable runs get longer and longer, as your number of amplifiers get more and more, you need a device in the middle to actually power all those amplifiers. And the UA bias T is the device that will do that for you. Next very important component is the passive splitter / combiner, the UA221. It is a reversible design which enables splitting or combining RF signals. Okay, it has a maximum input level of plus 30 dB, but most importantly, because it is a passive device, you have to account for in the range of 3 to 3.5 dB of insertion loss. So the moment you have this device in your system, either doing combining or doing distribution, splitting, combining, distribution, you have to account for 3 dB of insertion loss. Okay, and when you buy them, you get 2. I'll just hang on to this slide, because what's important with this is that it is reversible. So in fact, if you're using them in a splitter kind of mode, you will actually get your antenna will be connected here, and then this will split it. These 2 ports here will split them out. And you can reverse it as a combiner, so you can have the 2 antennas coming in here and coming in here, and then this one output becomes the combiner. But there is one thing that you need to remember with this device, and that is when you are combining 2 antennas, this side there is a DC blocking capacitor, and that is a fix which needs to be done in your tech shop. So basically, you unscrew this device, that capacitor needs to be removed. The details for that and a small video is also available up on the Shure website. It's also available in the UA221 manual. So if you ever require to use this device as a splitter, you're fine to use it as it is. If you need to use it as a combiner, you need to make sure that that DC blocking component has been removed. Now this is a typical setup. For example, we have 2 inline amplifiers. That's one here and here and here. And we have a Axin digital device. They're connected to antenna A and antenna B. Now, on the inline amplifier, like we said, there are 2 gain selector switches, +6 and +12. Since we are using the Axin digital, we don't require any power supply in the middle to power the device, because the Axin digital or the ULXD, for example, can power these devices. There is biased DC current that comes out from the antenna outputs. They also have an overload LED indication. So in case you're hitting it with too much power, there is an overload light which will come in on that. When I say too much power, I mean on the receive front. In case the receiving end is overloading the amplifier, then that red light will go off, and it's an indication that your receive power is too high. So it is now compatible with Shure wireless systems and can also be used along with the active antenna distribution system. So like the 845 and the 844. Also comes with a adapter that can have it wall mounted or desk mounted, or various mounting options are there for this as well. And again, just to remember that you will use this amplifier not only this amplifier and the amplifier that's on the fish plate antenna, you'll use that only to compensate for cable loss. There's absolutely no other area that you will use these amplifiers for. So you go back to that cable chart, the cable loss chart. From there, you select the cable that you're going to use, the distance that you're going to use, you calculate the loss, and then you use the inline amplifier to make up for that loss. But again, keeping in mind that the loss along any one of these paths, so path A or path B, needs to be kept at 3 dB, or worst case scenario, I'd say, is under 5. Okay, this is our next scenario where now we are seriously running a very long cable. In this case, we need to make up by using additional inline amplifiers. And to power those inline amplifiers, we need a bias T. By default, the bias power that is provided by like the Axon Digital or the ULXD can power up to 2 devices. Now, considering that because they provide 150 milliamperes of power. Now, considering from this slide, we have an active antenna here. We have an active antenna here. So these are 2 devices. And now, if this is a very long cable run, you might require maybe 1 or 2 more inline amplifiers. So to power 2 inline amplifiers along with the antenna amplifier, you require this bias T device. Yeah. There's no other way. Otherwise, if you don't have this device, then you're not supplying power to all 3 components. You will be able to power at the most 2 units. There's also, one thing to note is that there is barely any insertion loss with the bias T. It's in fact below 1 dB. 0.8 odd to be exact is the insertion loss from this device. So again, that's something that you need to take into account when you calculate your link budget. Now, putting this, here's a typical calculation that you will do. So my reception antenna A, I have consider the cable that I am using. Say if I lose 7 dB here, I lose 7 dB odd here. But using these 2 amplifiers, I can actually make up that gain. So in this kind of situation, I think all you need to do is keep maybe this diagram in your mind and then just replace these 7 dB figures over here with the actual amount that you're losing because of the cable, and accordingly make up from the inline amplifier. If you require the inline amplifier, if you don't, then make it up from the amplifier on the antenna. So coming back to that same formula, which is the antenna system gain should be the gain of the antenna plus whatever booster you're using minus the cable loss and minus the split loss. And again, the golden number is that it needs to be kept under 5 dB of total loss. Now, all the options that we considered before this are great, but they are to an extent limited by distance. And the only solution that you can get for very large distances is something known as RF over fiber. Now, it is a potential solution for very long cable runs, and basically it converts the RF signal to fiber optic. And once you're in fiber optic, basically you can go for a couple of kilometers. The one drawback of this is that there is a little the bandwidth of the RF signal is a little reduced. So you have to be a little careful about. You have to, in fact, be a little more careful about things like antenna placement, etc., because the amount of bandwidth that the fiber optic converter sends is less than not using a fiber optic converter. That's the only small drawback of it. But to an extent, when you need to send sometimes kilometers of distance, this is the only realistic solution, let's say. Now let's take a look at some antenna distribution for larger installations, and we'll also take a look at some practical examples of this. Couple of important considerations are how many systems are you using? 2 or more, 3 or more, 4 or more, 5 or more. And why this is important is because using 3 or more devices, you do not want to get into a situation where you are running, multiple antennas. Because for any of you all that came to the previous webinar, which was about and types of antennas and placements of antennas, the one thing that we saw there is that at all costs you want to avoid a situation where you have like an antenna, farm. You don't want all these antennas bunched up together, because each of them interacts with each other, and that basically destroys to an extent the polar pattern that the antenna was designed for. And if you end up destroying the polar pattern that the antenna was designed for, your system's not going to work the way it is supposed to work. Second is, are there any hidden or remote receivers? You very often have a receiver closet. It can be somewhere in some other room completely. Very normal for TV stations, broadcast rooms to have this, where they'll have one giant room which will have all the the mixers, the speakers, the RF equipment, and the antennas will be outside. So you need to pull antenna cable from all over the building sometimes into that one room, which sometimes can get into several tens, hundreds of meters sometimes. So this is an important consideration. And next is, do you require long range operation? So the design would be very different for a broadcast studio, which is maybe has an area of maybe 2,000 odd square feet. And the design might be very different if you're getting into a large football arena, and now you require coverage to actually happen in an area that might be 20,000 square feet, let's say. Yeah. So the design, these three main considerations are very important when designing the system. Now, why is antenna distribution important? Firstly, it prevents, and most importantly, it prevents interference between closely placed receiver antennas. This is what I spoke about earlier. This is the antenna farm, which you want to avoid at all costs. Okay. It grossly reduces the amount of equipment and cabling required. Yeah, in this picture, you've got 12 Shure receivers, and consider that each receiver has 2 antennas. That's 24 antennas. Would you rather use 24 antennas at 24 sets of cable, or just bring all that down into 2 antennas? Yeah. And lastly, basically uses one pair of antennas, so one set or one pair of antennas for the entire system. The other reason that you want to get into active, in this case, active antenna distribution is basically any of the passive devices give you a certain amount, give you 3 dB of insertion loss, whereas that insertion loss is now it's almost like your device is connected directly to the antenna. It does not see the distributor in the middle. So there are a lot of filters, a lot of amplifiers in the middle, which kind of do the job of making up that gain, to basically to make sure that whatever's coming to the antenna comes straight to the to the device. So that's the role of the distributor to an extent. And this is a little bit of science behind why the splitter is actually required. And the reason is that antennas that are spaced especially receive antennas that are spaced very close to each other, their polar pattern starts to get very altered and distorted, let's say. Um, um, and that's the reason why you do not want to get into the situation where you have multiple antennas all in a very close proximity. So as you can see from this diagram, here's the antenna, and what you're seeing is actually the effect of multiple antennas, in the same in very close proximity to this one antenna. So it's something that needs to be avoided by all circumstances. Now let's get into a very simple distribution feed. So passive splitter feeds one pair of antennas to two diversity receivers, and the splitter now feeds all the antenna feeds to the 4 or up to 5 diversity receivers. In this case, we are having a look at the ULXD. This is a pretty simple, straightforward setup. As opposed to this, if you're using the passive UA221 device, this is what your split will look like. So it's very important. I'll just put in a quick note about the reason why you split them like this, and that is to maintain your diversity. And when we talk about diversity, it's the fact that each device has two antennas, and the reason for it having two antennas is that you want at least one of the two antennas to pick up the signal from the transmitter the best possible. So you will always split, for example, over here, antenna A comes to the splitter. From here, one output goes to the A input of this device, and the other one goes to the A input of this device. And similarly with antenna B, but because it's a passive device, you have to account for this 3 dB insertion loss. So in this kind of situation, you'd calculate the cable loss here, the cable loss here, the cable loss along all the green lines, and you would also add 3 dB for here and 3 dB for here. So when I say the 5 dB loss per RF cable length, which means from this antenna down this way till here is one path. So this path needs to be under 3 dB or under 5 dB, worst case. And this path also needs to be under 5. And similarly, this path here under 5 and this part here under 5. Now these are antenna distribution amplifiers. So these are active distributors. So they basically make sure that whatever RF signal comes into the device, the same amount gets distributed to various devices below it, but without any loss. So this is why these devices are very important. And to make it more clear, instead of then all these little BNC ports here, you'd have to use like independent passive splitters, and then each passive split, like we said, gives you that 3 dB of loss. So this is the kind of device that you want to use for multiple devices. Okay, now this is again a little larger system. This is an active distribution system whereby you have antenna B and antenna A coming into the distributor, and each of the outputs here feed all the antenna B's here and feed, in this case, all the antenna A's here. Very simple, very straightforward setup. in this diagram, you can actually see that we are using two distribution systems, that is one here and one here, to actually provide a signal to multiple ULXD, in this case it's ULXD devices. So you actually see that the antennas are actually connected only to this one device. We use the cascade out from here and here to go into the input of the second device. And now the second device gives RF signal to all these. The first device gives RF signal to all these. So this is a two-level active distribution system. This now is a system which is much, much larger. So you can actually see now, if you calculate, you've got 1, 2, 3, 4 devices here. Even if you could calculate these as the ULXD quads, so that's 4, 4, 4, 4. So that's, what is this? 16 channels over here, 16 times 1, 2, 3, 4, 16 times 4 devices all running from a pair of antennas. This is where antenna distribution comes into. This is the real power of antenna distribution, and it basically, even the signal loss to an extent from this first distributor to this distributor to this is very, very negligible, and this is because they are all active distros. You can't even imagine doing a system like this with all passive distributors. Next to impossible. Another way to actually do the distribution is using cascading. So here you can see the Axon digital device. You have antenna A and B connected to the A and B ports here. And you have C and D, which actually cascade the RF signal to the second. One thing to remember, that for Axon digital and for the newer digital equipment, you can cascade only up to 2 levels via the cascade ports, no more than that. In the previous analog devices, you used to be able to do more. But then again, you have to remember, for example, this is only an Axon digital dual device. If you have 4 channels, so if it's a quad device, that means you can use 2 devices quad, so 8 channels, and just cascade it once. Which is actually, if you think of it, it goes back to the same of the older analog devices. The same number of channels, but just in 2 racks and 1 level of cascading. A quick antenna distribution checklist once more. Keep the gain and loss to under, plus minus 5 dB, as close to 5 as possible. Use as few antennas as is practically possible. Specify quality wireless systems for receiver RF performance. Again, very, very important. And very most important, I think the most important of all of these is to calculate the RF gain structure of the antenna system. There is no other way. You cannot guess. It's not something that can be guessed. It has to be calculated. Now let's get into some examples of multi-room antenna distribution. Just follow my the laser pointer that I have on the screen, just to guide you. Now we have a room. This is a typical 2-room antenna distribution system. We have a room A and we have a room B. Okay. One very important consideration is, in order to maintain diversity, you need to have both the antennas in each room. So that's to even say, if you have 10 rooms and one mic is supposed to work in 10 rooms, you want both the antennas of that receiver to be in all 10 rooms. Okay. So in this case, you have, say, let's start from here, antenna A going through this splitter here. And again, just remember, I say splitter combiner, but it's the device is interchangeable. So I'm still talking about the UA221 in this case. So the antenna A coming in here, antenna A coming in here, it gets combined over here, and now it goes out to the distribution. And similarly, antenna B from here and antenna B from here gets combined and comes into this. Now, when you calculate the RF link budget over here, you calculate this entire. So for A, you'll be calculating this antenna, all this cabling, the loss here, all this cabling, and all this cabling. Entire thing till it comes to the until it comes to the distro. Now that entire thing you want to be under 5. Okay, so this is simple two two room setup. A little small consideration I'll give you for basically placing the antennas in these rooms, and especially if the rooms are not divided by, say, a concrete structure. For example, in a large ballroom, you have like air walls, and you basically need those antennas to work independently and simultaneously. It's very important to now select the correct types of amplifiers. So in fact, in this kind of situation, if I ask you, what do you think will be the medium barrier between these two rooms? Your answer should be that it should be at least a concrete wall, so that these antennas from here don't interact with these antennas from here. If we were using these omnidirectional UA8 antennas, if this was actually like an air wall or a wooden partition, or those partitions that you have in ballrooms, then you would practically turn these into directional amplifiers so that they only interact with the stuff that's happening in this room, and to an extent are blocked from all the interaction that's happening here. Okay. This is now a setup for a 3-room system. So room A, room B, room C. When designing these rooms, the first thing is always to just place the antennas. Okay, so you place A, B, A, B, A, B. Okay, full diversity, that's all your antennas. Now you need to figure out antenna A and antenna A need to be combined with this antenna A, and similarly B needs to be combined with this B. Okay, so for antenna, this first two antennas get combined using a device here. You add the inline amplifier again if you require the inline amplifier to make up for cable loss. It now gets combined with this antenna A. Again, in case you require to make up for cable loss, you have another inline amplifier here. And again, remember, just like the distributor or any of the higher model digital RF devices, you can chain up. It gives you enough power to turn on 2 of these inline amplifiers. If now you had a 4th room and you need to add 1 more amplifier, that's when over here you would place a bias T. Yeah, so in this example, pretty straightforward, but you're considering that you're not doing more than 2 levels of combination. Yeah, which we'll actually see what happens when we move to a 4-room system. Here we go. Now in this case, we are using the 864 wall-mounted antenna, which is mainly used in our corporate installations. So here is now where you need to figure out whether a bias T is required or bias T is not required. So again, the reason why you already have a bias T over here is that because it's a corporate ballroom, these distances, like you can see here, will be in the range of about 100 to 150 feet. Yeah, and 150 feet of this Belden 9913 cable, you need to now do all these calculations. So it's not a really easy job. It's something that you'd have to, have specifications from an architect or from a designer as to, cable ducts are going here and the wiring is going to be this. And then as a designer, it's up to you to now spec what is the best quality cable to be used. A lot of consideration. What is the size of the duct? Are there a lot of bends? If there are a lot of bends, how do you accommodate for do you use a little more rigid cable? Do you use a little more flexible cable, etc.? So a lot of those considerations now come in to a system like this. This is now a typical 4-room scenario. And now as you can see, this little rectangle here and here, this is the bias T. And the reason we are using the bias T now is because we have 4 antennas being combined because of 4 separate rooms. So if you see on any channel, for example, let's just look at this antenna B going down here. You have one inline amp here, one inline amp over here, and you have on this side another two inline amps going to the B antenna on this side. So now you've got four devices. All of those need to be powered by the bias D. And similarly on the A channel. So now you can get a instance to see how complicated those calculations are going to be, because for say the B antenna system, you need to calculate this going through here, going through here, going through here, going through here, and coming back to this over here. So this is the entire calculation that needs to be in the range of 5 dB. And these are very real world situations. We get requests for these calculations quite regularly. Now we're just going to take a look at something with regards to modern technology, and that's the Axon Digital and Quadversity, and where it can actually help out in a situation like this. Now, the Quadversity mode in Axon Digital, once you put the device in Quadversity, you have actually access to all these 4 antenna ports at the back. So which means you can place 4 antennas in 4 different places of a stage or a theater or a boardroom, and the device intelligently looks at all 4 ports to see what is happening, and then accordingly demodulates the signal coming in. By the way, if you guys have any questions so far, you're welcome to mention your questions in the on the right hand side. You'll see a Q&A tab. Above that, there's a tab for polls, so you can attend those polls and list out all your questions, and I'll try my best to answer as many of those questions that I can. Okay, this is a typical theater scenario where you can have the Quadversity. Now you consider this as 2 rooms, but you actually have 2 antennas in the front on stage, and you have 2 antennas backstage, because very often the thing that troubles artists the most is that they're fine when they're on stage, but backstage suddenly they feel that their mics are cutting out, or there's no RF, then they start panicking. This is a very common scenario for the use of Quadversity. And where it's important is because if you had to have this antenna and this antenna here, you would have to have a combiner here, which means 3 dB loss. So in this kind of system, there's no you mitigate that 3 dB loss by getting the device into Quadversity mode. It's a very important feature and very used feature of the Axon Digital system. Another situation is this large field, playground, sporting event where you can have 4 antennas in 4 corners. Again, anything to reduce that 3 dB loss that might be here and here in order to join, say, these 2 antennas and these 2 antennas. This is now a very typical large, I think this is taken from a casino, very large setup. And as you can see, the paths, this is how you would typically design it. Once you have like an AutoCAD drawing or something, you would actually plot it to scale on the device, on the drawing itself. So you have the entire path for antenna A, where you'll have your combiners or distributors, where you'll have your inline amplifiers, etc., all the way up to the antenna. Similarly here, all the way up to the antenna. And you mark your various components. So your UA221s, your inline amplifiers, your bias Ts, everything has to be marked on a diagram like this. So it's only you can calculate that actual length once you plot it like this. Now you know this exact length here, this exact length, this exact length, and so on. This is also a very large project, which basically you see you have antennas that need to be positioned at these 4 locations. So location 1, location 2, location 3, location 4. Now these are almost like a what you call it, like a theme park, Disney World kind of setup. So again, very large decentralized kind of coverage areas where the real math and the technology now needs to be taken care of, and you need to actually do the calculations very accurately for something like this. Now, a distributed antenna system is also something that's it's a little bit outside our scope at the moment, simply because we are not. I'll do a webinar one day on DAS systems, which are basically distributed antenna systems. But this is basically what it kind of looks like, where you have a pair of devices being fed from a pair of combiners, and those going out to various types of antennas. So you have a wall-mounted antenna, you have got an Omni UA8, and again maybe another, various combinations and different types of antennas. And as you can see, you have different lengths of these antenna cables. So this is a subject for a whole other day, but also very interesting, but a little bit of a complicated situation. Instead of the passive device that we used earlier, now here have an active device. And these basically will help you combine multiple receive antennas close to unity gain because of internal signal combining. If you need two of these if you want diversity, because each device will combine one path of antenna. So if you want to do two paths for diversity, then you need two of these. And DC bias is also active for this device. So you don't, in this case, require like a bias T device. Large scale antenna combining. So you have, 4 rooms. This is a typical like a 4-room setup. So 4 channels, 1 antenna in each room, 4 channels, antenna B in each room. So antenna, you can cover 4 rooms with this, all coming back to a centralized location that feeds this ULXD rack. I want to just run you through a few tools that can be used for they are online tools which basically assist you with this calculation. One is the wireless mic remote antennas tool. So here you basically, this is all available on the Shure website. If you just enter the distance that you're using and what kind of antennas you want, it actually shows you what should your cable length be, what amplifier setting you should be using, and what devices you cannot use it with. So suffice to say that if you cannot use it with this device, you can use it with everything else. The reason you cannot use these directly is because the BLX, QLX, SLX don't provide bias, antenna bias. So if you want to use it with this device, you will then need to use a bias T before that, or you'll need to get into an active distribution system. So this is the option 1. This is option 2. So if you use this cable, you can go to this length, you can add this much power. Or the length 2 is if you do 19 meters, you can add so much power to it. This is the setup. Option 3. Okay. This is another page where it gives you, this is another calculator which gives you all the accessories that are required for you to build your system. So for example, the QLXD in G50 band, I want 10 devices. Am I rack mounting them? Yes or no? Do I need remote antennas? Yes or no? And what are my approximate cable lengths? So here I've just entered, for the sake of it, up to 125 feet. And I'm using directional antennas. Now this breaks down all the components that you require. So, I require UA844 pluses, 2 of them, 5 devices connected to each. That goes through a UA221 and feeds 2 sets of antennas. Again, depending on the amount of power that I require. In case I require to power this device, then I can use this, the inline amp here. These are the 3 links. I'll leave this slide on for a little while so you guys can note these down. But also I've noticed if you just go to the Shure website and you type in online calculators, you'll get a page with about 5 calculators and all these links will show up there. This link is not from the Shure website, but I find this to be a very helpful link because this helps you calculate everything from Times Microwave, all the cables made by Times Microwave. So yeah, just go to Google and type in Shure online calculators, and all these there are 5 calculators which will pop up for you. Ah, we're done. Let's move to some questions.
Okay, so we have some questions with us. The first one to begin with is Mr. XYZ asks, can buying a good cable reduce the requirements of inline amplifiers?
That is the most important consideration, when you're building your system, because you can have equipments in, like, lakhs of rupees, very expensive systems, and you should not be skimping on a bad quality cable. So the bare minimum should be a 213U low loss cable, which gives you that, yes, it is expensive, but which gives you the 100 feet run of that cable will give you a loss of just 3 dB. So, which means if you're using it on a large stage, and you say you have monitor console, and you need to, for whatever reason, you need to run the antenna to the other side of the stage, you can actually do it with this cable without any amplification or any stuff in the middle. It's a very important consideration. In fact, very good question.
Excellent. Moving on to the next question, it's from Prashra Singh. There are actually 3 questions, so I'll go one by one. Question number
Yeah.
1 is there absolutely no difference between the cascade out and the other 4 RF out ports behind the 844 Plus or the 845 5S?
The difference is the bias that it supports, that it provides. So that is the difference there.
Got it.
Other than that, they're pretty much the same.
Cool. Second question from him is, do we get a shrunk RF spectrum as we go on cascading the 844 Plus?
It's not a shrunk RF spectrum, but you have to be careful of the number of levels of distribution that you do, because with each level of distribution, you do in fact bring up the RF noise a little bit. So that's why it's not recommended to go beyond 3 levels of distribution. So one master, one feeding a second layer, and that second layer feeding a third layer. But it should not go, in most, I would say, practical circumstances, you do not need to go beyond 2 levels of distribution. But if you do, you can go 3, but you have to be careful that you do bring up the noise floor to a certain amount. So that has to be careful. You have to be careful about that.
Okay. Third question from him is, what are the limits of RF boosting and the best place in the signal chain to boost it, considering signal to noise ratio?
You always boost directly at the antenna, because and again, RF boosting, RF amplification, you do it at the antenna because you don't want to pick up all the noise from the cable, and then boost it on the other side. So you want to get that bump directly at you're going to get that help basically directly at the antenna. So yeah, considering signal to noise ratio, and in our circumstance, you don't even say signal to noise ratio. The term is generally carrier to noise ratio. So that is I know that that's basically the term that you should be using, and you need to basically have that amplification wherever you do it needs to be as close to the antenna as possible, or as close to like a passive splitter as possible. It should never be like on the just before you connect the cable into the receiver, because now you've picked up all the noise from the antenna, you've picked up all the loss from the cable, and now you're boosting the entire signal along with that noise. So it defeats the entire purpose of using that amplifier.
Cool. So we have 1 more minute to go. We'll quickly take a couple of more questions.
Yeah.
Question from Mr. Pankaj. What is the major factor to be counted when antenna is placed in the ceiling?
Firstly is the line of sight. Even if you place it in the ceiling, you have to be able to see the antenna. And I mean physically see it without any obstruction. And that's why we use our our wall mount antennas, because they're not, they don't look as what's the correct word, as obtrusive as, like, a fish plate which is black. Okay, it might not look great in a ballroom, in a corporate boardroom, and that's why you use these wall mount antennas. So again, even when you place the antenna in the ceiling, you need to be able to, if you're standing with the transmitter in your hand, or if it's on your waist like a body pack, from there physically you have to be able to see the antenna. That is a very important consideration. And then the calculations basically stay the same. So you still need to calculate the cable length. You still need to calculate, whether you need amplification anywhere. All that calculations still stay the same.
Excellent. Yeah, yeah. So it's very important that the antenna is visible to the transmitter.
Yeah.
It cannot be above the ceiling. It cannot be hidden anywhere. कोई
No.
लुका छुपी नहीं चलेगी. ट्रांसमीटर और एंटेना के बीच में एक लाइन ऑफ साइट सीधी बन जानी चाहिए.
Right, right, right.
Excellent. Moving
We
on
can
to the,
yeah, we can take a few more questions actually. I know we finished the webinar a little late, but I'm okay to go for another
not
5-6
many.
minutes.
We have three more questions. So
Cool,
coming
cool.
on to Mr. Prabhakar's question, is there a
Right.
programmable software for RF where we can draw the room on the floor design and then we
Right.
design our wireless units according to that?
Great question. Unfortunately, not at the moment that I know of. But it's pretty simple if you have like if you have like a blueprint, even if it's a PDF or a AutoCAD blueprint with you on a computer or something. It's pretty easy to just sketch those lengths out, and if it's AutoCAD, it's even better because then it's to scale. So even if you sketch something out, you can actually calculate the lengths that it will be. So unfortunately, you still need to go and do that via CAD. But that's a good suggestion. Maybe we can suggest it to Shaw and see if they'll make a software to do that. That'll be good.
Cool. Moving on to the question from Mr. Manjunath. Can we use two BLX and two SLX with the antenna distribution? Or
Yeah.
should we use only one particular model with the antenna distribution?
That's also a good question. Basically, the antenna distribution that you have, the most important factor there is to see is the bandwidth of the distributor. So is it a narrow bandwidth? Is it wide band? So is it covering the entire UHF spectrum? What comes after the distributor does not really matter. So it only matters if your distributor is not wideband, and then you have devices that do not fit in that band that the distributor is for. In that case, it's a problem. But in a case where you have, say, you can have two BLX, you can have two SLX, you can have multiple devices. As long as your distributor is a wideband distributor, it will cover, it will do the job for all of the devices. That's not a problem.
Yeah, just to clarify a bit, the BLX system has only internal antennas,
Internal antennas, yeah.
and yeah, so it wouldn't be able to be used along with the distribution system.
Yeah.
Just so that it's clear.
Yeah, the BLX is more
Uh,
also for very small. Yeah, it doesn't typically fall into the pro-ish kind of category, so it's more in a tighter corporate ballroom. But mentioning that it has, yes, an internal antenna, that's great. But the fact is that that antenna still needs to be seen by the transmitter. So you cannot hide the unit under a table or in a cupboard, because it won't work. So it still needs to be to an extent visible to the person or to the transmitter, so that it will actually, that line of sight is maintained. That still has to be, that's still like, paramount.
right.
Other than that, as far as devices, like you can have, you know, 5 units of one of a SLX in one band. You can have 5 units of some, other stuff in another band, and it won't be a problem to connect them. That's possible.
All right. Moving to Mr. Seturaman's question, is it possible to provide installed microphone system for 4 lecture halls, one above the other in 4 level of floors, combining all the microphone system using one gear in place? This is so that scalability and combining the lecture hall is possible when more audience are to be addressed from one lecture hall.
So if I understand this question correctly, you basically, let's consider using one microphone. There are two options. Now, the first thing is if you want that one microphone to work in any of the lecture halls. So you want it to work on the ground floor, first floor, second floor, and third floor, but you don't want to change any infrastructure. You just want to go up to the second floor and you want to start talking and using it. Yes, that's basically where a system like this comes into play. So I can basically take my one microphone to, and that's also to an extent how like news broadcasters work. So they have one setup of their equipment, and then like a news broadcaster for say the time slot of 7 to 8 in the morning will talk from one area, and for the time slot of 11 to 12 they'll go to some completely other area of the same building and talk from there. But they're carrying their same body packs and their same microphones with them. All those systems basically come to back to a centralized console, and that's where the actual on off and the switch on or switch off to what feed has to go where, that all happens from the console. So like you said, as far as scalability, this is exactly the solution where you have basically one room which has your infrastructure, and then you basically pull cabling and all that through the building, so you don't need to keep shifting your infrastructure. And this is just if we talk with one mic, considering that you have like say you have two say presenter microphones and maybe 4 microphones for question and answers. That's 6. So you have now one room with these 6 receivers, and you have a distribution system through the building or through the lecture halls, like he mentioned, and you can actually use the same 6, pretty much anywhere. And in a situation where say all of the 4 rooms are full, you can actually talk say from the ground room, and all that goes into your console, and then the console distributes it to the speaker system on the second, third, and the fourth lecture room, and you just broadcast the video. So yep, that's definitely that's exactly where a solution like this is used.
Cool. So we have
more to that point. Sorry, I'll just add one more thing. More to that point is that you don't need to reinstall 6 or 4 of that microphones in every single room. So you install one set of them, and you just distribute the antennas through the entire building, so to say. So that's a very good question, though. Excellent question.
Cool. So I think the last couple of questions, I'll just club them together because they're related. So the question is, if I want to buy a new wireless, what are the spectrum considerations that I should take care of for India? And are there going to be any frequency restrictions in this country?
That is an excellent question. And firstly, if you you have to be aware that firstly the changing what would you call it, landscape of RF across the world is firstly that you are losing out on the 700 megahertz band. There is no question about it. It will happen. When it happens, we don't know, but it is going to happen. And most countries in the world, like the UK, most of Europe, all of the US, all of Australia, Japan, China, are not allowed to use beyond 650 megahertz. Yep, that's it. And that is going to happen in India because the 650 megahertz onwards is prime real estate for communication. The government can sell that for billions of dollars. And the reason for that is that those waves provide the best propagation. They have the best propagation features. So bending, around corners, reflections, which are most important for emergency services. So police, ambulance, disaster management, all that kind of stuff, all falls in that 650 onwards band. And that's the reason. And you also have like the 4G and the 5G guys also fighting for that band. So it's a very, very precious commodity for the government of any country, and more so the government of India. So when that happens, any equipment that is 650 and above, safest at the moment would go below the 600s. So to keep your, say, if you have mics and in-ears, keep your mics between, the 500 to the mid 550, and keep your in-ears between 6 and 650. That would be a very safe option in my opinion. And just to make everyone aware that we've, as part of Shure, we've been aware of this situation for quite a while. And I think 2 years ago, we stopped importing equipment that was, beyond or touching the 700s or beyond that. And even our in-ear monitors PSM 1000s that we import now, are all in a very safe, situation. Anyone that has equipment that runs into the 700s, you can almost guarantee that if and when that law gets passed, that equipment will have to be either sold, or a buyback kind of scenario will have to happen. There's no option. You will not be able to operate that equipment.
So just to make it clear and simple for people who are interested in buying new wireless, so if you buy from an authorized dealer or a distributor in the country, so you will get the right frequency product, the right band product, because they are only importing which is as per the what is allowed in this region. So I think that would be the safest and easiest approach if you want to buy new wireless products from Shure.
Yeah.
So that kind of closes our Q&A, and then Fali, if you could just take them through the rest of.
So guys, if there's any information that you'll, any further questions that y'all want to ask, you can either forward it to india@shure.com. Once we get it, we'll send you a direct reply. This is the Talent LMS website, and this is now for our South Asia region. So for everyone that's maybe not aware, we are in the South. We are now Shure South Asia, which is India, Bangladesh, Nepal, Bhutan, Sri Lanka, and I believe it's Maldives. So this is now our online training portal. So this is the website. If you want to take a minute, I'll just leave this slide on so you all can write it down. And if anyone misses it out, you can just email us at this india@shure.com, and we'll make sure to get back to you. This is where any of the global webinars that are done, which happen generally every Wednesday, if I'm not mistaken, the recordings of those webinars come up on this webinars page in a few days. So if you miss a webinar, especially the global stuff, don't worry about it. You can access it from this page in a few days. Our stuff, the stuff that we do in South Asia, that generally goes online in a few days again, and that link will be made available once we have it. All right. Thank you very much. Thank you, Dave, for moderating this session, and thank you everyone for attending. And I will see you on Friday. Friday, just for information, is a webinar on the microphone range from Shure. So we go through the SM, we go through the PGAs, the SM, the betas, and the KSM microphones. So it'll be a nice, interesting session. Thank you very much again for attending, and stay safe. We'll see you soon.
Thank you.